Okay, so we're going to start off with waves that include pulses and normal transversal and longitudinal waves, and also electromagnetic radiation. Electromagnetic radiation is light waves. Okay, did you write those three? Okay, let's just quickly go over them. The first one is F equals 1 over big T. F is frequency. Frequency in English basically means the number of waves per second. So imagine you're doing the following. Imagine you have a rope in your hand and you can jerk the rope up and down. You'll see there's pulses and waves. A pulse is just something like this. A pulse is just one loop, while a wave is a pulse, a top end of a pulse and a bottom end. So if you take a rope or a hose pipe or something and you jerk it up and down, you'll create waves. Can you visualize that?
Yes.
I'm not going to worry about the equation for pulses. They're exactly the same as those for waves. So frequency is just the number of waves that you can produce per second. So maybe you can produce 5 waves per second. Okay, and that's called period, big T. Sorry, waves, frequency is in hertz, which is H_Z. Period is in seconds, and that's basically the time it takes for one wave to form. How long does it take for one wave to be created? Screenshot that. Those are very important definitions. So I can work out the frequency of the wave by taking 1 and dividing it with the time it takes for one wave to form. Okay, that's the first equation. You got that? So
Yes.
write it down. Okay, then we have V equals D over delta T. V is velocity, and that is in meters per second. Meters times seconds to the power of -1. And D is just distance, and that's in meters. And T is time in seconds. Write that down. Velocity is the speed of the wave, basically. So how fast is the wave moving? Well, you can take the distance the wave has moved and divide it by the time. But this equation, you know, in math, you use this one. Distance, time, seconds. Remember that? So the velocity is the speed in math. Speed is distance divided by time. Velocity is just a vector. So we don't use speed. Okay, and the last equation, we're going to do that one last. Velocity is F lambda. So there's another way to calculate the speed of the wave. That's the velocity of the wave. That is in meters per second. And F is frequency of the wave. And lambda is wavelength. Now, wavelength is in meter and frequency is in hertz. Okay, so write that down. And you need to have a paper with those 3 equations in front of you. We're going to use them soon. Tell me when I can start.
Okay.
We're just going to do a little bit of theory on pulses. Okay, pulses. Now, this drawing at the bottom here represents a pulse. So imagine you've got that rope or hose pipe in your hand. If it's lying on the grass, on the floor, it's in a position of rest. It's doing nothing. But if you jerk it up, it makes a pulse, a bubble up, and that bubble will travel in a certain direction. So that's called a pulse. So if you just jerk it up once, there will be like a bubble traveling on the floor. Who of you have done that actually, physically? Have done that? Taken a rope, yeah, or a hose pipe and just jerk it up and make a pulse, and the pulse runs along the road on the floor. Okay, so now the height of that pulse, that distance there, is called the amplitude. And that the distance between the first part going up and the second part is called pulse length. So that's not very difficult. So if you've got a pulse there, it goes up. That's called the distance of the pulse. That distance, pulse length, and that part there is called amplitude. Right, that's not very difficult. And it's all in meters. You're not allowed to use any other unit. You used to use meter. So now you can actually determine the pulse speed if you want to. So if you have a pulse here, just quickly, and that pulse has traveled 8 meters in 0.5 seconds. We can determine the velocity of the pulse. It's the distance it traveled over the time. The distance was 8 meters and the time is 0.5 seconds. And that is 16 meters per second. Are you happy with that?
Yeah.
Okay, good. Just basics. And then in this part of the chapter, there's only, apart from this, knowing the amplitude and the pulse length, actually descriptions for a sketch, basically. You have to understand one principle called superposition. So it works the following. Okay. 2 or more pulses can go through the same medium. In other words, you can have 2 pulses. So you've got one person standing on the one side of the rope and another person standing on the other side of the rope, and they can both create a pulse. So if someone creates a pulse on this side and it's moving in that direction, and someone's got the other end of the rope and it's moving in that direction, those 2 pulses will meet. When they meet, it's called superposition. 2 or more pulses can pass through the same medium at the same time and the same place. When they do interact with each other to form a different disturbance, the result is called the principle of superposition. Now, you get 2 types of superposition. This is theory that's very important. You get constructive interference and destructive interference. Now, look at these drawings. I mean, you're going to catch it in a second. If 2 pulses are both going up and they're traveling towards one another, superposition is going to take place. And the result is what? If this one was 1 meter high and that one was also 1 meter high, the new pulse when they meet will be 2 meters. So they will actually build one another up. Constructive interference. And after that 2 meter high pulse, they will move away each one in their own direction. Does that make sense? Yes. Okay, obviously the reverse is true. If both pulses are showing towards the bottom or bulging towards the bottom and they move towards one another, when they interfere, it's called constructive interference because they're building one another up. So if this was 0.5 meters and this one was 0.3 meters, the superposition will be 0.8 meters. Does that make sense? And afterwards, they'll move away. This is called constructive because they're building one another up. You also get destructive interference. So if we have 2 pulses, the one is 0.2 meters and going to the right, and the other one is 0.2 meters going to the left, what will happen? The pulses will destruct one another and there will be no pulse. It will be just 0. And afterwards, they'll move into different directions. This 0.2 will move in that direction, and this 0.2 will move in that direction. Okay, let's assume that we have a 0.5 meter pulse and a 0.2 meter pulse. One is going up and the other one's going down. When they meet, they will interfere. This is called destructive interference because they're breaking one another down in height. And the result will be what? Who can tell me what the result will be of that pulse? Or the amplitude? Is it not?
Would it be 0.3?
Yeah, 0.3 meter. And then afterwards, once they pass one another, this one will be 0.5 again, and this one will be 0.2. So that 0.3 is called the amplitude of this pulse that's interfered. This is not difficult. Would you agree? No.
Yes.
Easy peasy. Okay, good. There's an example. There's a pulse A, and the height is 1 meter. So the amplitude of A is 1 meter, and the amplitude of B is 1 meter, and they are actually going to crash or interfere. Okay, so now when they interfere, it's called constructive interference. They build one another up, and the combined pulse is 2 meters. Do you agree? The amplitude of that is 2 meters. And then afterwards, they move away from one another. Okay. So I want to know, in the first drawing, this one here, pulse A, I want to know if it took 0.2 seconds to reach what? 3 meters. What is the speed of the pulse? Give me an equation. Remember, you have to write the equation, otherwise you won't get marked. Give me a equation for that speed, or you can use, if they use speed, you can still use that velocity one, but you don't have to give direction. V equals D over, okay, let's say delta D over delta T. You're going to use D over delta T also. You don't have to use delta. Delta is just change in distance, but you can use distance over change in time. Right. What's the velocity? What's the distance? 3 meters. What is the velocity? Sorry, the time, 0.2. So the velocity is what? Help me. Is it not 15? Quickly put that in a calculator. Happy?
So how did you get 15?
I divided it. 3 with 0.2.
Okay.
Well, that's what that equation tells me to do. I've got other ways of doing it. I multiply with 5 bottom and top. I get 15.
Okay, I see now. Thank you.
Okay, happy with this?
Yes.
Okay. Okay, I'm going to test you quickly. There's a pulse. It's moving in that direction. It completed 18 centimeters. And the time it took to complete that 18 centimeters was 0.1. Oh, 1.8 is going to be dumb. 1.5 seconds. I want to know, what is the velocity of the pulse? Quickly do that. What would the velocity of the pulse be?
Will it be 120?
No, I don't think so. You must give an equation, otherwise you get 0 marks. V equals D over
Okay.
delta T.
Okay.
What is the
Yes.
distance? Please, the answer is not 18.
0.18.
Yes. The distance must be in meters. So I'm going to take the 18 centimeters and divide it with 100 to get meters. And I'm going to divide that with a time of 0.15. Okay, redo that, please. I get 1.2 meters per second. Is that correct?
Yes, sir.
Okay, excellent. Now, you're going to read this section on pulses. Why? Because you're going to write a test and they're going to test you on pulses. But pulses aren't, you're never going to see that again. Everything we've learned about pulses, we can just apply with waves, because a wave is just a continuous pulse. A pulse is that one jerk you did in the hose pipe or in the rope. But if you continue to jerk the hose pipe up and down, or there's waves going to form like that. And we're going to do the main section of this chapter is actually about waves, not pulses. Pulses are just there to introduce waves. Right, so this is the wave. There's a wave example. Right, now I'm going to teach you a couple of things. Questions. The first thing I want to know is, what is the amplitude? What is the amplitude of the wave? Now, the amplitude is the distance from this position of rest upwards. Can anyone tell me what that amplitude would be? Remember, the answer must be in meters.
3.6 meters.
Now, look at the y-axis. I don't know if you can see that, but that's in centimeters. And so the x-axis is also in centimeters. So that is 6 divided by 100 to get meters, isn't it? 0.06 meters. 6 is wrong. 6 centimeters is wrong. Okay. Happy?
Yes.
2, I want to know what is the wavelength. Okay, you don't have to know this yet. Okay, I'm going to show you how to actually see how long a wave is. If we start there and we have an up and a downward movement and we end there, that is a total wavelength. So I'll show you in yellow. There's one wave. That's one wave way of calculating a wavelength. Right from the position rest, right through your upper curve. It's called trough, and I don't know what they call that position there in top. Trough is bottom, crown is top. So you got a top part and a bottom part. That's one way of calculating the wavelength. Okay, so let's just get that quickly. Is that 12 centimeters? Can you see that? Is it clear enough? Hello?
Yes.
So that is 12 divided by 100. And that is 0.12 meters. That's your wavelength. There's another way to determine the wavelength. You can calculate the wavelength from one of the crown areas to the another one. And that distance is starting at, it's 3 here, and it's 15 there. Can you see that?
Yes.
So that's a distance from C to F, which is 2 crowns. Okay, so you can also calculate that. That is 15 minus 3, so that is 12 centimeters. And that gives me the same answer as 0.12 meters. Also, you can have worked from the bottom part, yeah, from E all the way to 21. So that starts at 9 and ends at 21. And the difference also there is 12 centimeters. So there's different ways that you can calculate the wavelength. Is that fine? Yeah. Difficult? No. Happy?
No.
No.
Yes.
Okay, happy. Good. Okay, I'm just going to clear this. Okay, now we're going to start doing other questions. The first thing I want to know is what is the frequency of the wave? One more. So let's write that. 3. What is the frequency? Okay, well, they've given that to us. The frequency is 25 hertz. Awesome. Number 4. I want to know what is the period of the wave. What is period again? Period is the time it takes for one wave to form. Okay, we have an equation here. Your frequency is, let me just write with another color. Your frequency is 1 divided by t, and t is the period. So t is 1 over f. Do you understand what I've done there? I've made t the subject of the equation. Please tell me that you understand what I've done.
Yes, sir.
Okay, so t is 1 over 25. And type that in your calculator. That is 0.04 seconds. It's not difficult. Happy?
Yes.
Okay, last question. What is the speed of the wave? Okay, there's 2 equations. Now you have to be very careful. The one is v equals distance over time. And the other one is velocity is frequency times lambda. You can help me with that lambda. What's lambda again? It's the wave length. the length of one wave. Okay, now look at this. I'm going to make a little drawing here. Here is one wave. Let's say that's one wave. If this distance from that point to that point is 2 meters, and this wave travels 200 meters from your house all the way to what? To the other side of the road. Then the wavelength is 2 meters, because that's the length of the wave. But the distance the wave travels is 200 meters. So which one of those two values do we have from the drawing? Do we have the distance it traveled, or do we have the wavelength?
Oh,
Which one of those do we have? In other words, do we have distance or do we have lambda? If you look at the drawing. We worked one of them out already. Don't we have this? What is that?
the distance of the wave.
No, it's the wavelength. We calculated that in number 2. So we can't really use this equation because we don't have the distance this wave traveled. We only have the length of the wave. So the velocity is the frequency, which is 25 hertz, times the wavelength, which is 0.12. We've calculated that. So that's 25 times 0.12. And that is 3 meters per second. There was another way of calculating it, but I want you to distinguish between these two things: the distance a wave travels and the physical length of the wave. The physical length of the wave, which you can sometimes measure from a drawing. We could have measured this. Okay, how do you feel about this? It's okay. There's a lot of new things now that you have.
Yeah.
Okay, good. Happy?
Yes.
Okay, photograph this or screenshot this. We do another example. Can I continue?
Yes.
Okay, look at the y and x axis. Now, in this example, they are both in meters. Then I tell you, it takes 0.6 seconds for 3 waves to form. Determine the following. The first thing I want to know is, number 1, what is the amplitude? And number 2, I want to know what is the wavelength. Quickly do those two. What is the amplitude? Okay, it's not difficult. Answer. Anyone? Wave amplitude.
3
3 what?
meters.
3 meters. Correct. Wavelength, please.
Wavelengths will be
6 meters.
6 meters. Okay, that was the easiest to start there and end there. That's one wavelength, and that's 6. Or you could have started on top there, ended there. That's like 1.5 to 7.5, 1.5 to 7.5. That's also 6. Or you can start it anywhere. You can start there and end there. That's also one wave. Oh, sorry, end there. And that's between 3 and 9, which is also 6 meters. Are you with me?
Yes, sir.
Yes.
Good. I want to know, what is the frequency. What is the frequency of the wave? What is frequency? What does frequency mean? Let's just ask ourselves, what does it mean? It's the number of waves in 1 second. Now, frequency means it's the number of waves produced or that passes a point in 1 second. So you can use an equation if you want to, you can use some logic. Because they tell you that there is 0.6 seconds for 3 waves. So I'll show you a couple of ways to do this. I just want to test your logic. Just look at that and tell me what is the frequency of those waves.
Um, 0.0.
Is it 0.2?
0.2 is the time it takes for one wave to be formed, isn't it? But that's not
Yes.
frequency. Okay, I understand what you've done, but you've now not given F. In this equation, you've calculated T.
Okay.
Okay, so let's just do, is it Kelvin?
Yes, sir.
Let's just do Kelvin's method. Kelvin said, look, there's the equation. Frequency is 1 over T. If I can only find T, and T is the time it takes for one wave to form. So one wave, well, if 3 waves to 1 wave, I divide with 3 this side. So he divided with 3 that side. That's basically what he did. No. And then I get 0.2 seconds. So the frequency is 1 over 0.2. What's that? Isn't that 5 hertz? So that's one way of doing it. First, to calculate T. Look at that. The other method was to say, look, it takes 0.6 seconds for 3 waves to form. I want to know, how long does it take? How many waves forms in 1 second? 1 second is the number of waves in 1 second is the frequency. And then you just make this X. So I need to convert that to 1. And there's various ways of doing it, but you can also cross multiply. Then you get 0.6x equals 3. And then if you divide that, you get 5 hertz. The red method is nice because you first calculate the time it takes for one wave to form, which was 0.2 seconds. Are you happy with that? This is very important. Okay, so can I delete that or make that small? Zelna.
Yes.
Okay, right. Number 4. I want to know what is the period of the waves. Period. That's T. T equals 1 over F. Well, we've done that actually. You can say it's 0.2 seconds from 3, or you can just recalculate it, which is 1 over 5. And that was 0.2 seconds. Remember, this one is in seconds. Frequency is in hertz. Okay, number 5. I want to know what is the speed of that wave. What is the wave speed? Speed of that wave. There's 2 equations. V is d over delta t, or V is f lambda. Which one are you going to use?
So I use the one on the right, the
F
PFY.
flat. Yes. So my velocity is the frequency, which was 5 hertz, and lambda was what? 6 meters, isn't it? We were calculated that
Yes.
already. And that is 30 meters per second. Awesome. Okay, remember, if they say speed, you don't have to give direction. If they say velocity, you have to give direction. Good. Example 2. Right now, this is sound interesting. Look at this. Look at the y-axis. It's given in centimeters. That's wrong. I need to convert that into meters. And then the x-axis is given in time, but it's time, which is times 10 to the power of minus 2 seconds. What does that mean? So whenever you have a time, then you must multiply it by 10 to the power of minus 2. So now the first question, okay, what is the amplitude? Well, let's help one another there. Can anyone tell me what the amplitude of that wave is? Well, we're going to assume, this is a bit dumb. We're going to assume that is 1 to 3 centimeters, isn't it? I didn't give you values there. That was quite unfair. So let's just put them in there. 1, 2, 3, minus 1, minus 2, minus 3. Okay, are you happy with that? So let's start again. What is the amplitude of that wave?
3 meters.
Now, 3 centimeters is how many marks? 0 marks.
0.3.
3 divided by 100.
0.03.
0.03 meters. Number 2, I want to know, what is the period? The period is the time it takes for one wave to form. Think about it. It's not difficult. Try and find one wave first. Give me an equation.
X equals 1 over t, which you then change into t equals 1 over a.
Okay. Right, but I have a problem. I don't have if.
So then
Because let's ask ourselves just a logic question. That isn't wrong. That's fine. But the problem is I don't have if. What about a bit of logic? What is t? Help me again. Explain what is t.
time,
Time for what?
time that the wavelength.
One wave. Time for one wave to be produced or pass a point. The thing is, I have time on the x-axis. So if I can find one wave there, I can actually read the time it took for one wave to form, which is what?
6
6 times 10 to the power minus 2 seconds, isn't it?
yes.
Leave it like that. Or you can write 0.0061, 06. You can type that into your calculator, in other words. And it will give you a decimal, 0.066. But both answers are correct. Okay. Right, so that I can just do that. I don't have to do an equation because there's some logic there. And then number 3 is, what is the frequency of the wave? Now I can use the equation. The frequency is 1 over big T. I have to write the equation, otherwise I lose marks. Okay, help me. Frequency is 1 over 0.06. And that is what? 16.67 hertz. HZ. Right. Last question on this one. 4. What is the wave speed? Speed of the wave. On your own. Okay. Who's not spoken yet? Calvin, Saskia. Equation. Come, Saskia. What's the equation?
So would it be the velocity equals distance divided by time?
Nope. You can use that one, but you not in this not in the sketch. Come, what do we have? Don't we have the wavelength?
Oh, wait, yes, we do.
We have the frequency, which is 16,67. The wavelength they've given you is 0,4 meters. Look, from the one top crown to the other crown is 0,4 meters. See that?
Yes.
So I've got that 16,66666 in my calculator. I'm going to multiply it with 0.4. Then I get 6,67 meters per second. We are going to use the wave. We're going to use this formula. V equals D over delta T. We're going to use with sound waves a lot because the sound wave travels over a distance. This is just a transversal wave that's on a drawing. So you could have used that equation. You could have said the time it takes for, you could have used the 0,4 in another method. There is a way of using it, but I don't want to show you that. I want to show you, we're going to use that with sound waves. Next one. Okay, this diagram below is a graphical representation of a transverse wave. We'll talk about transverse and longitudinal waves soon. That shows you how a wave varies periodically in time. Okay, but that's not a problem. The wave moves at a speed of 2.2 meters per second, and the wavelength is 3,9 meters per second. Use this table to answer a couple of questions. And the first question is, what is the amplitude? And the second question is going to be, what is, what can I ask? Give 2 points in phase. You don't know what that is. So fine, I'll show you that. And then number 3, I want to know, what is the frequency? Okay, what's amplitude? Quickly help me, amplitude.
It's 0,05.
Huh?
0,4.
Isn't that 40 up there? So it's 40 centimeters divided by 100, which is 0,4 meters. That's the amplitude of the wave.
Thank you.
Give 2 points in phase. 2 points in phase is just 2 points that are the exact same spot. And I don't even, and the only 2 points in phase is A and E. In phase mean they are exactly at the same spot. So if I had a point here on top here, which was, say for instance, called H, then B and H is also in phase. If I had a bottom spot here called K, then C and K was also in phase. But I only have A and E. Happy? In phase simply means that if I draw the wave between those 2 points, it exactly makes one wave. Okay, anyway. Right. I want to know what is the frequency of the wave. There's 2 ways of doing it. I don't know. Quickly take a half minute or a minute and think about it. Give me equations, please. Frequency is 1 over time. Velocity is frequency times lambda.
Okay.
What about using this one? Because the frequency is the velocity divided by lambda, isn't it? If I divide lambda away, I get velocity divided by lambda is frequency. I have the velocity. They've given that to me. It's 2.2. I have the wavelength. They've given that. That's 3,9. What do we have there? 0,56. 0,56 hertz. That's very low. Very low frequency. So now we can actually determine number 4. What is the value of D? Who of you can do that now? What is the value of D? Is it D exactly a spot where one wave is completed? Is that, can you see that? So D is on the x-axis, and that represents time. So basically what I'm asking, how long will it take for one wave to be completed? And that is big T. T is 1 over F, and that is 1 over 0,56. You see, this is 1.77, 1,77 seconds. Zelna, you sent me something. Oh. I'm still recording it. Okay, let's do the final example. Okay, let's quickly do this one. The diagram below shows a water wave moving from left to right across the dam surface. The time between 2 consecutive trouts is 0,9 seconds. 2 consecutive trouts, let's say E and J. 2 consecutive trouts is 0,9 seconds. So therefore, the time it takes for one wave to form is 0,9 seconds. That's one wave there. From the bottom there to the bottom there is one wave. Or you can do A to E also is one wave. Okay, so the amplitude here is 1,3 divided by 2. What's that? 0,65 meters. That's the amplitude. Okay, what else can they ask us? Well, wavelength. What is our wavelength? Well, they give you this little section here, which is half a wave, is 2 meters. The wavelength is therefore 2 times 2 because there's 2 of those sections in one full wave, and that is 4 meters. Then they can also ask you, what is the frequency? Okay. The frequency is 1 over T, and that is 1 over 0,9. You get to take that and put that in your calculator. Don't try and work it out. That is 1, oops, not 11, 1,11 hertz. And then they can ask you, what is the wave speed? And I can work it out. Speed is F lambda. The frequency is 1,11 hertz. And I'm going to times that with the wavelength, which we calculated as 4. That gives me 4,44 meters per second. Snap that. And then we're finished.